Okay, so this is our warm-up question for the day. This just kind of covers a few pieces of material that we covered last week. On Friday last week, we were introduced to the idea of three-space vectors. So just talking about vectors that have that z component and how we can translate those 2D concepts and formulas into 3D concepts and formulas. So we're going to do a little bit of practice with that here. Can somebody tell me how they calculated the magnitude of A, vector A? Awesome. So we square each component. Just wait till we're all ready here. Okay. So we square each component and then we take the square root. We will express that as a simplified radical if possible. So in exact form, what'd you guys get? Yes. Yeah, so you end up getting root 75, which we can take out. We can split into 25 times 3, and then take the square root of the 25 part, which gives us 5 root 3. Okay? All right. Number 2, A dot B. Can somebody tell me how we do A dot B with three-space Cartesian vectors? We do all three vectors. Okay. Okay, so we'll do the multiple of the x components plus the multiple of the y components plus the multiple of the z components. And it looks like here we get, what's that, negative 28 plus 10, negative 18, yeah, negative 15. Perfect. And then we are tasked with finding the angle, finding the angle between A and B. How would we do this? How do we find the angle between two vectors? Yeah, so we're actually going to use the geometric dot product formula to help us out. And basically what we do is we take the geometric dot product formula where we use cosine of theta. Oops. Brian? Magnitude of A. Okay, and then we divide out each of the magnitudes of these vectors. So I'm going to divide this by magnitude of A times the magnitude of B. And then we'll take the cos inverse of that answer. Okay, so A dot B we actually already have from part 2. It's negative 15. Magnitude of A we have from the first part here. Since we're taking the cos inverse of this anyways, you can write root 75 or you can write 5 root 3. It doesn't really matter. And then what'd you guys get for your magnitude of B? Square root of 29. And then we will do cos inverse of that expression. Or I guess I'll just do it up here so I don't have to rewrite it. Let's do cos inverse, and theta equals? Beautiful. Okay, there's a couple of things that I can do to maybe check my work here. If I wanted to potentially plug this 108.76 back in here, if I'm confident in my calculation of the magnitude of A and magnitude of B, I can see if my answer from that gives me the dot product that I calculated above. But you do need to at least have some component of correct work there, right? Like if I don't know that magnitude of A and magnitude of B are correct, that's a little bit tougher. If I knew that the dot product was correct, I could maybe do negative 15 divided by the cos of 108 and see if it's equal to the magnitudes multiplied. Like you can check a left side, right side type thing there. Okay, just to make sure. All right, any questions on those 3 questions? We're okay? Okay. All right, so today we're going to learn about what we call the cross product. So I referenced this actually in one of our previous lessons last week when we were taking up some homework. So we talked about can we multiply vectors? And the answer was actually no, we can't multiply vectors. But there's two operations that we do with vectors. One is the dot product, which we know kind of tells us how one vector is strengthening another vector. And the other one is the cross product. So you'll see they both kind of look like multiplication symbols, but they are different than just simply multiplying. So the cross product is basically done so that we can get a vector that is what we call orthogonal. Or another word that we are more familiar with is a perpendicular vector. But we usually use the word orthogonal when we're talking about vectors. Okay, and this result is not only perpendicular to one of the vectors, but it's actually perpendicular to both vectors that we cross. So if I have two vectors in space here, these could be arranged in any way, my trusty cup of vectors. My third vector is actually going to be the one that's like perpendicular to both of these things. So it's going to give me one like this. So no matter where this vector is, it's going to be perpendicular to both of them, this cross product vector that we get. Okay? All right. So geometric formula. You guys okay back there?
I thought that was so funny.
Okay. Happy to entertain.
Like I would like you like homework like after the credit. It's funny, okay, Lauren?
All right. Shh. Quiet, guys. Okay, so we're going to do geometric and Cartesian cross product today. So the cross product is actually very similar to the dot product. Couple little differences. So we'll get A cross B is equal to magnitude of A multiplied by magnitude of B multiplied by sine of theta. And then we have this little n hat guy. So this part right here, do this in another color. This part right here is going to be the part that gives me the magnitude of the normal vector. So it will tell me the length, depending on the length of A and B. So this part gives me magnitude. And this part right here, this part gives me direction. And the direction is perpendicular to both A and B. And what we usually need to state is whether our cross product goes out of whatever we're talking about. So if it's like a board or if we're just talking about our paper, it goes out or inward, right? Because if I have my two vectors, I can have a normal that comes out this way, or I could have a normal that comes out this way. It depends which way I cross these guys. So there's a little trick that I'm going to show you so that you can figure that one out. You might know it from doing torque in physics, but this will be our normal vector, or a vector that is perpendicular or orthogonal to A and B, yep. And then we need to tell whether this is going out or in.
Can you just explain what you mean by out?
I will show you in our next example. Okay, I think the idea of out or in is actually probably the easiest to understand when we think about a screw. If I screw a screw into a wooden board a certain way, and if I go one way, it's screwing into the board, but if I turn it the opposite way, it's actually coming out of the board depending on which way I'm screwing it. So that's kind of what we're talking about when we say cross product, right? So is it going inward or outward? That kind of idea. Good? Can I flip? Okay. All right. So uses for the cross product are, this is just like a little snippet of uses for the cross product, but analysis of seismic activity, computer graphics, and especially animation to illustrate lighting relative to a given plane. So all of the like realistic animations that you see, they have to make sure the angles of their lights are all, you know, making sense and stuff like that. Torque, magnetic fields on an electric charge, and many more. But these are some of the big ones. Okay, so the easiest way that we can tell whether our vector is coming out from the two vectors or going in is if we use what's called the right-hand rule. So even if you're left-handed, you're going to use your right hand, okay? And we are going to arrange our right hand so that it's positioned in line with our vector that is first in our cross product. So in this example number 1 right here, you guys will see that we're doing A cross B, right? So I'm going to arrange my right hand rather than doing this, because this is where I'm aligning my hand with the B vector. I actually want to be able to align my hand with the vector that we start with, and I want to be able to curl my fingers toward the other vector. So I can't do this, because if I curl my fingers, I'm not curling toward B. So if I do this, I can curl my vectors, my fingers toward vector. These are my vectors. I can curl my fingers toward vector B, and notice where my thumb is going. Is my thumb going in toward the board or out? Okay, so this one is going to be into the board. We'll get a normal vector to A and B, but it's going to be like into the board. Okay, so this is kind of the idea. If we think about this like in 3 space, here's my vector A and B. My normal vector, rather than going like out like this, is going to be on this side. It'll be going in. Does that make sense?
What if it was like this?
Yeah.
Oh, it'd be like this too.
The third vector, yeah.
Going this way.
Okay, so this guy right here, so we're aligning our hand with A. You'll notice that you have to be able to curve your fingers toward the other vector, and you'll notice that your thumb is pointing inward. So this one is going to be into the board. Or if you're doing it on a paper, it can be into the paper or whatever. Okay, now if we try the right-hand rule with B cross A, I'm aligning my fingers, my right hand with vector B so that I can curl my fingers toward vector A, and where is my thumb pointing? It's out. So B cross A is actually out of the board. Yep. Okay, so you need to align your right hand with the first vector that we're starting the cross product with, but you need to be able to curl your fingers toward the other vector that you're crossing it with. Yeah, you kind of have to. Does that make sense? Got it? Okay. Good? Any other questions on this guy? Okay. All right, I'm going to, actually, I'll ask you guys this right now. Is A cross B going to be the same thing as B cross A, given this information? No, it's not. So the dot product, I can do A dot B, and it will be the same thing as B dot A. However, A cross B will not be the exact same as B cross A. I will get a vector. My normal vector will be of the same magnitude. However, it will not be in the same direction. One of them will be into and one of them will be out of. Okay, so with that said, some properties of the cross product. Yes, it is quite long. Okay, so like I said here, guys, if I have U cross V, it's actually going to be equal to V cross U, but in the opposite direction, right? One will be into, one will be out of. So by putting that negative there, we account for that change in direction. Okay, the cross product is distributive. However, I want you guys to notice something with question 2 here. Question 2, you will notice that we've specifically put u in a special place in the expanded version. Why have I put u in front of both of these vectors in this expanded version when I did distributive property? It was at the beginning, okay? So it's actually important that I don't do v cross u and w cross u. I want to do u crossed with v plus u crossed with w. So that order is actually very important that we maintain that order, okay? Yes, exactly. So you'll see here, I have another example for you guys. If w is at the end, then I'm making sure that my w's in my expanded version here are at the end of those cross products, okay? Okay, and then these are both examples of the distributive property. Okay, so we just want to make sure we maintain the order of the vectors. Being crossed. Olivia?
When I'm looking at the textbook, they have a distributive and then two other words that describe vectors.
Associative and commutative.
Did you learn the other two?
Associative is this, number 4. Just means like if I'm multiplying a scalar, it doesn't matter which order, the order in which I do that. And then the dot product is the communicative property where we can do it in either order, but the cross product is not. Yeah. Okay, and this is called the associative property, where it basically just says if I'm multiplying in a scalar, I can do that in any order. So keep in mind, k is a scalar, it's not a vector. And I can do that times u first and then cross it with w, or I can do that scalar times w and then we can cross u by w, and that will all give me the same vector. But I just still want to make sure that I maintain that proper order, right? U is always going to be first and w will be last. Mark?
So does the dot product also have distributive properties?
Yes, it does. All right, so a couple other little properties that we can use to kind of help us with vectors. For the cross product, if u cross v is equal to the 0 vector, and u and v don't equal the 0 vector, we don't want to cross vectors if we're dealing with a 0 vector, then we will say u and v are collinear. Can someone remind us what this word means, collinear? Yes. Okay, so can someone remind us what happens when the dot product equals 0? What does that tell us about our vectors? That tells us that they're perpendicular. If the cross product equals the 0 vector, it tells us that they're parallel. Makes sense, right?
What if like u equals 0, but v doesn't?
Both of them can't equal the 0 vector, yeah. So tell me, why would the cross product of two parallel vectors equal the 0 vector? So they could be opposite vectors, they could be going in the same direction, right? Mark?
So it's supposed to find the perpendicular vector, but if they're collinear, like there's no perpendicular vector?
Right, so I need my space to be defined by like two vectors to find a vector that is defined that is perpendicular to both of them. This vector is the same if I have these two defined vectors, right? No matter where. I can put it over here if I want, but this is still the same vector, right? If these become parallel, now my normal vector could be anywhere. It could be any vector. It's undefined, right? So I can find any any perpendicular vector along these vectors, and it's just not defined. So that's why we get the 0 vector. Whereas if I have two defined vectors, there's only going to be one vector that's either, well, I guess two technically, but there's going to be the out of and into vector that's perpendicular to both of these, right? But as soon as they're parallel, I can have infinite vectors that are like perpendicular to these. So we want one single defined vector that's perpendicular to both. Olivia?
Oh, I was just wondering, because of the vectors, they have to be, it has to be in that angle that they need for it to be the.
No, it could be like, so we want to make sure that it's perpendicular to both, but it could be like over here. We'll usually always express this vector as if it's starting at 0, 0 anyway, so we move it so that it's expressed starting at the point 0, 0 or 0, 0, 0 if we're working in 3 space. Okay, and the other cool thing about the cross product is I can actually figure out the area of the parallelogram defined by vector u and vector v when they're arranged tail to tail if I take the magnitude of u cross v. So I actually get the magnitude of that whole parallelogram. So I'll show you guys a little picture of that. Okay, so you guys know how we do our little parallelogram method, and we do this. U crossed with v, if I take the magnitude of that, it actually gives me the area of this whole thing. U cross v gives me the normal vector, but if I take the magnitude of that normal vector, it actually is related to the area of that parallelogram. Oh, sorry.
Wouldn't just u times v give you the area?
We don't do u times v.
Oh yeah, true.
There's no such thing, right? It's either dot or cross.
What about if you took the absolute value of u times v?
There's no u times v.
Absolute value of u times absolute value of v.
And then you will get the magnitudes multiplied. And that's it.
Not the area?
No. Because the cross product takes into account the angle between them. If you just do the magnitude of u times the magnitude of v, it's just taking into account the lengths of those vectors, but we don't know what the angle is between those vectors, right?
Like, the area, it all cancels out like in a parallelogram.
What do you mean it all canceled out?
Like, if this is u and this is v, either way, if you multiply them like this, it goes this way anyways. Do you know what I mean?
No. You'll have to explain it to me after. Okay, we're going to do a couple examples here. So this is a geometric example for you guys, so I'm focusing in on the geometric formula that we discussed previously, which was this. Oh. And then this n hat is essentially where I just decide out of or into. So we can decide that right now. Let's take our right hand, and we're going to line it up with our first vector that we're starting to cross, which is A. And I want to make sure my fingers can curl toward B. So where is our thumb pointing? It's into. So we'll say into the board. Okay, and then we're just going to plug in the remaining things here. So I want magnitude of A, magnitude of B, and sine of the angle when they're arranged tail to tail. And we'll keep in mind that this is into the board, so we have to state that at the end with our answer. So if we take our right hand and we line it up with A, we have to curl toward B. Yeah. Perfect. Yep. It is 642.78, so we'll just say 0.8. Okay, guys, there's lots of conversations happening today and over the past week, I would say. So let's just be focused in here. Okay, if you have questions, ask them because other people might have the same questions as well. You can say into the board or into the paper since you guys are working on a paper. N is going to be the direction of the normal vector. So n is essentially just saying, like, is it going out or is it going in? Yep. No, we just have to use the right-hand rule and decide whether it's coming out or going in. Okay, not too bad. Pretty straightforward for that guy. Okay, can I flip? Okay, Cartesian vector formula. So, actually I don't know. Oh, I do have it underneath here. Perfect. Okay, this looks confusing. Okay, but essentially when we're observing the cross product and we're talking about Cartesian vectors, in order to find a normal vector, the x components are actually almost like what's happening. So the dot product, sorry, start again, fresh slate. The dot product looks at how common elements, like how the x's work together, how the y's work together, and how the z's work together to strengthen one another. The cross product is interested in how opposite pieces interact together of those vectors. So you'll notice for the x coordinate here that we actually use the y components and the z components, and that kind of helps us find like an opposite vector that's perpendicular to both of them. So we're not going to use this, but it's still good to kind of visually see what's going on here. But I'm going to show you guys a little trick that you can use. So you can still copy it, just so you have it. So you'll notice that there's kind of, do you guys see what pattern is kind of happening here? What's the pattern that's going on? Okay, so it's the two opposite vectors. What's that, Mark?
CX for A, and then CXY for B.
So you'll always notice with this second component here that the order gets reversed. But I'll kind of show you where this order comes from and why we have certain things in certain orders with this little trick. Yeah. Okay, so our little trick is this. We are going to take the vectors A and B, and we're going to arrange them on top of each other twice. So I'm going to have the x, y, z, and the x, y, z of both A and B kind of like stacked on top of each other here. Okay, so here's what I want. I'm going to put on top the vector that I'm crossing first. So if I'm doing A cross B, I'm going to put A on top. So it'll be AX, AY, AZ. And then I'm going to actually write it again, AX, AY, AZ. This might make a little bit more sense once we do it with actual numbers, but for now. And then we'll stack the vector that's being crossed with A on bottom, and we're going to write it twice. Okay, so again, this is when we're doing A crossed with B. If I was doing the opposite, I would put the B components on top and the A's on bottom. Okay, so I'm going to kind of focus here on some of the diagonals. And the diagonals are this. If I want the x component of my cross product, it's going to be this right-handed diagonal. So AY, BZ, subtracted with this left-handed diagonal right here.
Can't you just cross out the first two of the whole thing and the last two of the whole thing, and then just cross them?
Yeah, so I'm just laying the foundation for this right now. I'm just explaining where the formula comes from. So it'll be minus AZ BY, working like from the top to the bottom. Okay? The y component of this is going to be this diagonal, this first diagonal, that was bad, which is AZ BX minus this second diagonal right here. So AX BZ. And the Z component, actually I'm going to use purple for this one. One second, Ryan, hold your question till the end. Okay, will be this. Yep, that's okay. We use each component twice. Yep. By minus our last diagonal here, which is this guy. Ay times bz. So it's going to take a little bit of practice. It's totally okay. I'm just kind of showing you where the formula comes from. Again, what the big thing to remember here, shh, everyone listen. What the big thing to remember here is that if I'm finding the x component of the cross product, I'm interested in how the opposite parts of that vector are interacting. So I'm interested in how the y's and z's are interacting. And then if I'm finding the y component, I'm interested in how the z's and x's are interacting. And then if I'm finding the z component, I'm interested in how the x's and y's are interacting. Does the order of by and ax here matter? And ay and bz, or sorry, this should be bz, my mistake. Bx for that last one. Do those orders matter? As far as the multiplications, no, but I want this multiplication to be subtracted by this second multiplication here. So I can do those multiplications in either order, but the subtraction should remain the same. Aiden?
Can we just memorize the rule if we want to and not use the trick?
This looks like a lot more.
So this looks difficult right now, but once we do it with actual numbers, you guys will see that it's a lot easier than memorizing the formula. Okay?
For like x equals ay bz.
Yep.
Where do you get the bz? Oh, is it like the? Oh, never mind. It's like the one underneath. Right?
Yep. Yep. Okay, so don't freak out. We're going to do an example, and I think you guys will, once you practice it a couple times, you'll get the hang of it. Okay? Okay. All right, A cross C. So this is what I'm going to do, guys. I'm going to write my A vector twice. One, -2. And then I'm going to write my C vector twice. Okay, and you'll notice from our little thing that we did over here, do I use the AX, BX components or the AZ, BZ components that are on either end here? I actually don't use those. So if you wanted to, you could actually go ahead and just essentially cross out this and cross out this because we don't need it for our cross product. Okay, so if I'm doing A cross B, or A cross C, sorry, we're going to get a new vector, okay? The result of the cross product is a vector, so I'm using my square bracket. And now I think you guys will see how this becomes like a little bit easier. So I'm going to cross to the right. This is my multiple. Okay, I want everybody just looking up here for a second. I'll give you a second to copy it, but just watch while I do this, okay? Just so you're kind of following along. So I do, going from the left to the right, 1 times 4, and then I will subtract going from the right to the left on the opposite diagonal. So I will subtract 2 times -2. That gives me the x component. Okay, and then we're going to go to the next set of 4, and I'm going to do down to the right. That will be my y, and I'll subtract from the right down to the left on that opposite diagonal. So it'll be 7 times 4. And then last set of 4 right here, for the z component, I'm going down to the right, and I subtract going down toward the left. So it'll be 1, running out of room here, 1 times -1. Okay, so you guys can copy. Okay, we're going to practice it again. And then, no, you definitely don't. Once you get the hang of it, you can, for sure, like if you don't feel like you don't need to draw it. However, I will tell you that the most mistakes that I see is when people do cross product and they're not like careful about it. They end up messing it up. So it's up to you, but okay, and then we're just gonna simplify each little component here. So we get 4 plus 4, that gives us 8. We get 2 minus 28, which gives us -26. And then For our last one, we get 14 minus 4, which gives us 10.
Ms. Michaelis, why is the last, like the very last term in that, why is it's 1 times 4? I'm just looking at
Oh.
the,
Yeah, sorry, I erased it and oh no, it's -1, sorry.
yeah.
That was just my handwriting that I was misreading. So it's 1 times -1, my mistake. Thank you. And it still looks like 4 kind of, but yeah, so it should be 14, it should be 15. Yeah, thank you. Okay, how can I double check that this vector is in fact perpendicular to both A and C?
Dot product.
Right. So if I want to do a check, dot your normal vector, and, or sorry, with A, there's no B here. And see if it gives you 0. And dot it with C, and see if it gives you 0. If that happens, if you check the dot products of those, and each of them give you that scalar 0, you know that those two vectors are perpendicular. If one gives you 0 and one does not, that's a problem, right? It has to give you 0 for both dot products. Cool? Okay, let's try it again. Okay, so we want to do Z crossed with H. So I'm writing out Z. So the first vector that I'm crossing is actually the one that will be on top. So just make sure you write those in the correct order. And then the second vector, I will write that twice as well. Okay, and then we actually don't end up using these little pieces of this, so you can just actually cross those out. So we're actually interested in those middle pieces there. Okay, so see if you guys can do it here. I'll give you a little head start. Sarah?
For to check with the dot of like A dot N.
Yep.
Is N like hiding that? Or like what is
N is our new normal vector here. So N is the normal vector to A cross C. So we'll just call this like vector N. No problem. Okay, I'm going to start writing out my answer here. Should be 0 minus -7, so that'll be +7, right? Okay, questions on this one, guys? Mark? This is 0 actually, right? Because it's 3 times 0. No worries. Any other questions for this guy? Olivia?
Just explain again how you do check.
Check? Okay, so let's just do a quick, we'll do our check together here. I'm going to check. This is going to be, we'll call this our normal vector and this was z cross h right here. Okay, so this is going to be the normal vector that we get that is perpendicular to both z and h. So I'm going to check that z dotted with our normal vector is going to give us 0. So I would be taking my z components, or my vector z, the x, y, and z components, and multiplying them and adding them, so doing the dot product here. And I just want to check that each of these that I check is equal to 0. So I get negative 31 plus 21, that gives me negative 10, plus 10, which gives me 0. That's what we wanted. And then we're going to check h dotted with our new vector. So it will be 0 times 31 plus 2 times 7 plus 7 times negative 2. So we get 0 for the first one, and then this is positive 14 and negative 14. So we get 0 here.
You want 0 because that means it's perpendicular.
Yes. Yep, when the dot product gives you 0, that means that the vectors that you dotted were perpendicular to one another.
What happens if it would be perpendicular to one?
Then you probably made a mistake somehow. Okay? So this, guys, this check is actually key here because, again, like I said, the cross product, if you're not careful about your negatives and positives, you can make a mistake pretty easily. I'm sure some of you guys probably already saw that with like just little minute details here. So if you're not careful, it's always good to do that check at the end just to double check and make sure that your cross product was correct. Okay? All right, we're almost done here. Anything else before we move to the next one? Okay. So last two parts here, we are going to find the area of the parallelogram defined by A and B, vectors A and B. So in our properties earlier, you would have seen that the area of the parallelogram is actually the magnitude of A crossed with B. You can also do the magnitude of B crossed with A because we know those magnitudes are the same, the directions are just opposite. So this is what I'm interested in finding. If you happen to do B cross A, it will be fine because you're just finding the magnitude. So why don't we start with A cross B? Let's find that first. Okay, and then like we said before, we're not interested in these ends right here, so we can just cross those out. And we're going to do cross product here. So we should get 3 times 1 and negative 2 times 4, that's negative 8. Okay, I'm doing the multiplications ahead of time now, like in my head as I do it. And then 7 times 1 is 7. And then 7 times 4, 28, minus 3 times negative 2, negative 6. So we get our vector 11, negative 3, and positive 34. How do I find the magnitude of this?
You do the square root, you do it by negative here.
Okay.
Oh, that is, yeah, no, just, you just do 11 squared over root of 11.
Yep. So we're going to square root and do each component squared and added. Okay, careful with your negatives here, guys. We want to make sure that, like, if you're going to plug this all into your calculator or whatever, make sure that that negative gets included in your squared. We know that once I square each of these, I should be adding all positive numbers, okay? Because anything squared is going to be positive. So you should never be subtracting any values in underneath the root here. Okay, what did you guys get?
35.86.
Exactly. What's the exact value?
Root 1286.
Yes. Okay, so after you square them, you should get 1286. Can that be reduced anymore? Can we reduce this radical at all? A lot of your calculators, I think, do this for you, but you can check and see like if 16 goes in there or 4. Is this final? Okay, so this is going to be, we don't have units, but this is units squared. Okay, so even if you're not given this is measured in centimeters or whatever, you are going to say units squared at the end because that's how we calculate area, right? Area is going to be something squared. So square units, basically, is what we'll just say. Sarah.
So, like, the calculation for finding the area is like a little fuzzy. I don't think the same way when we calculate like all of them, but if it's like a parallelogram, why is it not just like the line going forward? Or we only have 1 point?
So when we just have like the lengths, the magnitudes of both vectors, we don't know what the angle is between those vectors. So we need to take into consideration the angle between those, which is why we use cross product. Okay? Okay, last one, and then you guys will have some time to work on your own stuff. Why don't you guys see if you can do this one? We're going to do A cross B, and then it's going to be dotted with A.
Isn't it just 0?
Oh, interesting. So Aiden says, isn't this just 0? Why would this be 0?
I don't know.
Okay. Well, if I do A cross B, what do I get? I get a vector that is,
Oh, perpendicular. And then if you dotted it with and, it gives, oh.
okay. So
That one is it.
just to reiterate, just so everyone can hear here, when I do A cross B, I get a vector that is perpendicular to both A and B. And we know that if I dot that with one of those vectors, then when I dot two vectors that are perpendicular, I get 0 from that, right? So I want you guys to prove that this is going to be 0. Do your cross product and then dot it and show me that it's 0. Okay, I'll give you a little head start before I start.
I got 0, I don't understand how it would be 0
So we have vector A cross B. We found it to be 11, -3, 34. And we want to dot it, guys. We want to dot it with A. And we're just checking to see if our prediction is correct. So we get 77 plus -9 plus 34 times -2, that's -68. And do we get 0? 0. It's a scalar, right? Because we're dotting a vector with another vector. When we dot, we get a scalar. When we cross, we get a vector. So we got a vector out of our cross product, but then we dotted it with another vector, which means we get scalar. Just as a little side note to you guys, sometimes you may not see these brackets. If I happen to see something like that, if I had something like this, let's just say I had something like this and I had all 3 vectors, how do I know which order to do this in?
So just left, right?
It's not left to right. Because if I have, what? But these are kind of both like a type of multiplication between vectors. So how do we? So there's a certain thing that I have to do first in both of these examples. We need to think about what we get from the dot product and what we get from a cross product. So if, let's suppose I did this first. What would I get from D, vector D dotted with vector E?
A scalar.
A scalar. Can I cross a vector and a scalar? No. So the only thing that makes sense is that I do this first. I do the cross product first, and then I dot that with my vector. Because I can't cross a vector and a scalar. Okay? So cross product first always. Okay, so this right here, that would be the first thing I do, the cross product. Okay, again, because if I do the dot product first, I get a scalar, And then I'm trying to cross a scalar and a vector, and I can't do that. I can only cross a vector with a vector. Okay, so that is what we want to make sure we do. We are working today on page 410, numbers 1 to 5, 7 to 11. It's right at the top of your lesson, right underneath the title. Also, you guys had some questions over the weekend. Tomorrow we have a quiz covering up to and including what we did on Friday. So up to and including like the projections and stuff that we did with applications of dot product. Okay, so cross product will not be on it. But just keep in mind, like our schedule, I'm just going to stop the video here.